Okay, so this is my physics exam 3 corrections. So yeah, 3. So the first one that I got wrong is number 3. It's an RC circuit is connected across an ideal battery through an open switch. The resistance and capacitance are in series. The switch is closed at time equals 0. Which of the following statements regarding the circuit is correct? And I initially put D, that the potential across the resistors and the potential difference across the capacitor are always equal. This was not true. It's not a true statement. And so the correct statement is actually C, and it's once the capacitor is fully charged, there is no current in the circuit, and that's just because once the capacitor is charged, basically you can't have electrons flowing across the capacitor because there's space there, and so they have to go back and forth, and so there's no appreciable current at that point. And so for 4, an electron moving in the direction of a uniform electric field, what happens to the potential energy of the electron? Is the electron moving to a location of lower or higher potential? And for this one, I put C. I put the potential energy decreases and higher with higher potential. And I think when I was picturing this in my mind, I just got B and C mixed up basically, because I was picturing it going into like a lower potential but like a higher potential energy, so that like the potential energy is going to increase, but I just didn't know how to put that into the words, I guess. And so I should have put B. The correct answer is B. The potential energy increases and the lower potential, because as it's stopping, it's going to have lower potential, but the potential energy is going to increase because it's fighting into that space where the potential energy is going to be higher. Okay. Okay. So for 7, I integrated incorrectly. I should have. I thought that I didn't realize that I was supposed to be using R, the radius, instead of just another ds, and so I just used ds instead of dr. But if I used dr, then my equation would have been correct. I had negative integral from point 0 to 3 to 42 of rho over 2 epsilon naught dr. Okay, so that was my original equation. This is correct when you solve for r. Okay, so basically you have negative rho over 2 epsilon naught out here, 0.023.042. Then you just have r dr, and so this is going to end up being negative rho over 2 epsilon naught times by 1/2 r squared from 0.023 to 0.042, and so this is just equal to negative rho over 4 epsilon naught of 0.042 squared minus 0.023 squared. And so this should give us an answer. And so this ends up coming out at negative 2.62 volts, and then let's see, and then I had this originally, but A has the higher potential. Okay. Okay. So okay. So the next one that I got wrong is 8. It's the one about the circuit. And so to solve this, first you start out on the battery go around, and so it would be 9. You come down here. This is going to continue, so it's going to be plus 6 because it's not the positive side, or the negative side is facing towards the positive side, so you're going to keep going, you keep adding, and then because this is also in that, you're going to add another 22, and then because it's IR is equal to V, you're going to multiply it by I. And this is all equal to 0 because of the Kirchhoff's law, whatever it is, the loop law. Okay, and so basically you have I is equal then to, let's see, so to 15 over 22, which is equal to 0.68, okay, amps. And then for the second part, you use this. You do the second loop. You did the outside. Now you're doing the inside, and so you do 6 volts plus, and so it's this one's 18 I equals 0 because you use this times by I, and you end up using this I, but or you don't. Okay, so I is equal to 6 over 18 is equal to 0.33 amps. And R1 is going from right to left, and then R2. Okay, so they're both going from right to left. They're both going from this side to that side to that side. Okay. Okay, so the next one I'm going to do is number 9. They initially give you the current at 0.022 amps, and they want the direction of the current in the 500 ohm resistor. Okay, so you start out and you find the resistance. So minus IR, 15 plus 10 minus I1 times 400 is equal to 0. And then from here you solve for IR. Let's see, it's going to be is equal to 5 plus, and then it's going to be 0.022 the amps. I guess I shouldn't do that, but it's 0.022 for the amps for the current of that times by the resistor, and so IR is equal to, okay, and this is going to end up equaling negative 13.8. Okay, and then so from here you do you work out the other loop, and you find that it's 30 minus 500 times 0.022 amps minus I1 plus 15 plus IR is equal to 0. Okay, that's just when you go around the loop. Okay. So then you find that 500 I1 is equal to 40 negative 45. 400 is equal to 11, so plus 11, and then minus plus 13.8. So minus 45 plus 1 minus plus. Okay, and so this is equal to negative 20.2 over 500 is equal to I1, the current for 1, and then this is equal to negative 0.0404 amps. Okay, and then from here, to find out how many amps you actually are going across that resistor, or you have, is equal to I minus I1, and so it would be 0.022, and then it's going to be plus because of the minus and negative, 0.0404, and then this is going to be equal to 0.62, and it's and then so the direction of the current in the 500 ohm resistor is going to be moving to the right. Okay. Okay. So the next one that I had to do was 10. They gave you the resistance was equal to 15,000 ohms, and then they gave you the voltage of the battery was equal to 24 volts, and then they gave you the time constant was equal to 24 times 10 to the negative 6 seconds. Okay, and then so they were asking for the capacitance for this. Okay, so the capacitance for this, you do your time constant is equal to RC, and then from there you just divide by R to get your capacitance. So your capacitance is equal to tau over R, which is equal to 24 times 10 to the negative 6 over 15,000, and this gives you what your capacitance is, and so it ends up being 1.6 times 10 to the negative 9th farads, or 1.6 nanofarads. I initially put that it was 1.6 nanofarads in the test. I didn't answer it exactly how I think you would have wanted it to be answered, but I had enough information to the point that I could answer it. So the next one I have to do is 11. An electron with an initial speed of 5.2 times 10 to the 6 meters per second is brought to rest by an electric field. What is the potential difference that stopped the electron? Okay, so using the equation that negative U is equal to QV, you also know that U is equal to work, and so you can do negative work is equal to QV. And then you also know that work can be equal to negative mv, or negative 1/2 mv squared. And so then just solving this for the voltage, you get that the voltage is equal to mv squared over 2q, and that it's negative. Then plugging everything in, you get that it's equal to negative 9.11 times 10 to the negative 31 times 5.2 times 10 to the 6 all over 2 times 1.6 times 10 to the negative 15, or 19 times 10 to the negative 19. And then when you plug everything in for this, you get that it is equal to negative 77 volts. Okay. Okay, so the next one I have to do is 12. They give you all these 4 capacitors in parallel together with a voltage of 50 volts going to the left, and so it hits 2 of them before it hits the other 2, and so those 2 basically get most of the charge. But it asks you how much. Assume that electrostatic. Okay, so it says that assume electrostatic equilibrium has been reached. How much energy does each individual capacitor store? Okay, and so from there you just get that. So you have to find an equation for it, and when capacitors are in parallel, you can just add them up together, and so you just do C1 times 0 is all equal to 0. And so solving for x, you get 65x minus 3250 plus 32x minus 1600 plus 48x plus 15x is all equal to 0. Solving this out, you get that 160x is equal to 4850. And then solving this out, you get the x is equal to 30.3. Okay. And so once you have your x, that's going to be what you're going to use. You're going to subtract that from the initial 50 when you're using this equation on all of your individual charges, basically, on all your individual total energies. And so doing this, I'll do the first one, but the rest of them are just repetitive, pretty much. So U is equal to 1/2 65 times 10 to the negative 6 times 50 minus 30.3 squared, and this is equal to 12.6 millijoules. And then this is 1, 2. Oh, why not? I'll just do all of them. 32 times 10 to the negative 6 times 50 minus 30.3. And you do this because they are in parallel together, and because they use up more of the voltage faster. 6.2 joules. U3 is equal to 6 times 30.3 squared is equal to 22 joules. And U4 is equal to 1/2 15 times 10 to the negative 6 times 30.3 squared is equal to 6.9 joules. Okay. Okay, and that's my corrections for the test.